Hello. Today I'm talking about the vector product or cross product. And I'm doing that because I've been teaching it recently and I looked at some textbooks and I decided they were all got it a bit backwards, really. So this is my title, The Vector Product Done Right, because I think there's a better way to do it. My title is to some extent a homage to this splendid book by Sheldon Axley. This is an undergraduate book, actually, but he's motivated in the same way that he thought linear algebra, at least in American universities, wasn't being done quite right. So he's used that as his title. And this book, by the way, is available for free. You can download it for free, although it's quite modern. So that's interesting. It's a nice book. Okay, so the vector product, there are two ways to think about it. There's the geometric view of it, which is this. So R cross rho, where R and rho are two vectors, is a vector, and its size is the size of R times the size of rho times sine theta, where theta is the angle between them. And its direction is in the direction of n hat, which is the unit vector orthogonal to both R and rho, as determined by the right-hand rule. So a right-hand rule, by the way, you're supposed to remember it with your fingers, aren't you, on your right hand? But I can never remember which finger's supposed to be which. So, excuse me. So I do it another way, which is to do with the right-hand screw thread. So I imagine I've got a screwdriver, and its blade here is pointing in the direction of R, and then I twist the screwdriver so that it's pointing in the direction of rho. And I imagine I'm driving a screw at the time, and the direction the screw goes in is the direction of n hat. So it's a right-hand screw thread, the way I think about it. Okay, it's a lovely view. It tells you everything you want to know about it, really, about a vector, how big it is and what direction it's pointing it in. And it's definitely the one you want to think about if you're thinking about things like how electrons move in the magnetic field. It's not all that easy to calculate it, actually, from that as a definition. So the other view is this one. It's just a piece of algebra. So here are our two vectors, and here is the cross product. That's pretty opaque, really. Looking at that gives you no clue, really, about what direction it's pointing in, and not much idea of what size it is either, really. So hopeless from the point of view of getting any intuition about it. But it's much easier to calculate. And it turns out also it's much easier to prove things from this. So let's see why that's true. So if we take this as a definition, as all the textbooks I looked at do, there are some problems with it. The first one, well, isn't really a problem, but it's a slight issue. There are, of course, two angles between R and rho. There's the small one and the big one. So the one that's bigger than 180, around the back, as it were. So if you took that one instead, then its sine is the negative of the sine of the smaller angle, but also n hat's negative. It goes in the other direction. So in this case, as you get the same answer, but in this case, the cross product and n hat are pointing in opposite directions. But there's a minus sign involved. So that's a slight issue, but not really a problem. The one that is a problem, though, is this. Suppose R and rho are parallel or antiparallel. Well, in that case, n hat is undefined. There are infinitely many unit vectors orthogonal to both R and rho. And you might say, well, that doesn't really matter because sine theta is zero in that case anyway, and so this thing's definitely zero. And that's sort of right, but it does matter a bit because it's very uncomfortable having a definition that depends on something that might be undefined. In fact, the situation is worse if one of R and rho is zero, because then not only is n hat undefined, but so is theta. And again, you may say, well, that doesn't really matter because one of these numbers is zero anyway, and so the cross product's zero. But it does matter because if you have something that's defined in terms of something that might be undefined and you want to construct a rigorous proof, sort of at every stage you have to worry whether these things that are appearing in your proof are defined or not. And if they're not, does it matter? So in the end, to produce a rigorous proof, you really have to change this definition. You have to put in this special clause that says the cross product is zero if R and rho are linearly dependent. And then if they're not, sine theta and n hat are defined, and you can define it that way. That's a bit messy. It means the proof has to have special cases in it. For example, if you've got two cross products involved in your theorem, then you've got four cases to consider. And also, it's really rather odd. As a programmer, I just hate the idea of having an if clause that depends on essentially a real number being zero. It's just very inelegant. But it also makes the proofs more difficult, as I say. Right, so before moving on, there are some angle words you might not know, which are rather cute. So I'm sure you know this one. An angle is acute if it's less than 90, obtuse if it's between 90 and 180. What you may not know is it's said to be convex if it's between 0 and 180. So if we're doing the vector product, we will always be assuming that theta is the convex angle between r and rho. And then you know that an angle is reflex if it's between 180 and 360. Similarly, I'm sure you know that two angles are complementary if they add to 90, supplementary if they add to 180. What you may not know is that they're explementary if they add to 360, which is rather cute. So if you've got the two angles that you might consider when you're taking the cross product of two vectors, one is convex and the other is reflex, and they are explementary. Okay, on we go. The algebraic definition has no such problems. Nothing particularly nasty happens if one of these is zero. There's another way to think about it, which is this. So in this thing is formally determined, IJK and the standard unit vectors here. So it's not really determined because these are vectors and these are scalars. But in terms of a piece of algebra, it's just the same really, because when you expand this, you get I times beta b gamma minus c beta, which is exactly this first component of the vector. So it works perfectly well. And it's a nice way to remember it. Okay, and as I say, it's much easier to prove all the things we need to prove from this definition. Well, it's either slightly easier or much easier to prove all the things we need from this definition than from the other one. And in particular, it's easier to prove the geometric definition from this one than the other way round. So what I believe is what we ought to do when we teach this is introduce the geometric definition first and discuss it and get some intuition about what it is about, and perhaps talking about electrons in magnetic fields, but then go back to this definition and prove that it's equivalent to the geometric one rather than the other way around. So let's just see how all that works. So one of the things you need to prove is that it's anti-commutative. If you swap r and rho, then you get the negative, and that's just shuffling letters around. So if you swap these two things, then you get the negative. It's just trivial algebra. And this is similar. If you multiply r by lambda, then you multiply the scalar product by lambda. And again, that's just shuffling letters around. You take lambda outside the bracket. This one is the one that's much more difficult to prove from the geometric view. And the textbooks that I looked at, most of them just assumed this, which is disgraceful in the maths textbook. And the other one had an attempt at proving it and made a hash of it. It is quite tricky. Here it's not, it's just trivial. Just the same, shuffling letters around. So R cross rho plus sigma is this lot. So rho plus sigma is alpha plus delta, beta plus epsilon, gamma plus zeta. And so you get this. And you expand the brackets and blah, 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 and out it comes. Just pause the video if you want to check it. This is another thing you want to prove. I'm assuming you know everything you need to know about the scalar product, except to say that actually the definition of this, that's mod r mod rho times cos theta, is subject to the same theoretical difficulty in that if one of r and rho is zero, then cos theta is undefined. But I'm not going to use that definition here. I don't need it. I'm going to use the other definition. So this is sum of the squares of the components of that vector. So that's that lot. Expand that, you get all the squares and all the cross terms. Then do the same thing here. So mod r squared is a squared plus b squared plus c squared. That's mod rho squared. And this is r dot rho. Expand that in the same way, sort of similar terms and the cross terms. And this one, all the squares and all the cross terms. And now you'll notice that those two cancel, those two cancel, and those two cancel. So we're left with exactly the same thing. So again, this is just shuffling letters around. There's nothing intellectually challenging here. Quite challenging to write it down without making any mistakes. But okay, I think I've got that right. Pause the video if you want to check it. So what we're left with then is to prove that if we make the definition this way, then this is a theorem, this geometric view. Right, so let's start with a linearly dependent case. So if r and rho are linearly dependent, then one of them is a multiple of the other. So let's assume it's that one, in which case, well, there you go. So lambda r is lambda a, lambda b, lambda c. And so the top term is b times lambda c minus c times lambda b, which is zero. So the whole thing's zero. That's easy enough. So now we're going to assume they're linearly independent. So they're both non-zero and they're not multiples of one another. So the first thing to do is to prove that it has the right length. And we use this theorem we've just proved. So, and now we can quote this theorem, this version of the scalar product because cos theta is defined, because we're assuming that R and rho are linearly independent at this point. And that's that. And so that. Um, so the slight subtlety here, I'm taking a square root, but that's okay because everything's positive. And we're assuming we're taking the convex angle here. Okay. Now we need to prove that it's pointing in the right direction. So the first thing to do is that it's on the right line. So it's either the left-hand rule or the right-hand rule, but it's at least orthogonal to both R and rho, and that's easy enough. We just take the dot product with one of them. So, for example, if we take the dot product with R, we get this. So it's A times the first component, and so on. Expand those, and then we say, oh look, those cancel, and those cancel, and so it's zero. So again, it's sort of completely trivial algebra, really. Right. So now we want to prove that it's the right-hand rule, not the left-hand rule. This is a little bit trickier. So again, we start with I, j, and k as being the standard unit vectors in the standard arrangement, and then I times j is indeed k, because look here. So I is just 1, 0, 0, and j is 0, 1, 0. So the only non-zero bits are a and beta. So we get all these are zero. So it's just 0, 0, 1, which is k. So we know one case where r dot rho is the right-hand rule. But look at this. This is a continuous function of r and rho. So that means if you just change r and rho a little bit, you're not going to change the cross product much. That's the key. So now let's do some visualization. So here is a little GeoGebra thingy. So r is the red vector, rho is the green vector, and the cross product is the blue one. And if I move A around a little bit, you'll see that the cross product only moves a little bit. So it's moving continuously as I continuously move A or I continuously move B. So I'm starting in a random place. And what I'm going to do is move A and B towards I and J, respectively. And as I do that, the cross product is going to move continuously. It's going to stay on this line, which is the line that's orthogonal to A and B. And this line is that sort of one side's the right-hand rule, and the other's left-hand rule. And so it's going to stay either right-handed or left-handed unless it gets to zero. So long as I move A and B, or R and rho, continuously in such a way that they remain linearly independent, then the cross product is going to stay on the same side of the line. So let's do that. So first I move A to I, like so. And we see that the cross product moves continuously. So the only problem here is if I happen to go through a scalar multiple of rho, and the worst case, if rho is actually a scalar multiple of I. Well, if that's the case, I just before I start, I just move B aside a bit. It's still a continuous move, and that's all right. Then I move A to I, and that's fine. And then I move B to J. And again, the only thing that can go wrong here is I might go through a multiple of what's now I. Well, if it is, I just go round it. There's plenty of room. So I can still move continuously from wherever B starts to J without going through a multiple of I. And when I've got there, of course, the cross product will be K. We know that. So when we've got there, the cross product is on the right-hand rule side of this line. So it must have been all along because it can't ever have moved. So it must have been so this must be the right-hand rule end. So there we are. In summary, if we make the algebraic view of the cross product the definition, everything drops out basically straightforwardly. This is not entirely straightforward, but it's not very difficult. Whereas the other way around, there are problems with all the proofs, some of them bigger than others. And so that's the way around you should do it. So there we are. Vector product done right. Hope you enjoyed it.